In the previous modules, we have discussed about the various creep deformation mechanisms and the metallurgical instabilities that takes place at high temperatures, which can be seen at elevated temperature test, that there is a sharp break or change in the slope at high temperatures, indicating that there are some structural instabilities, microstructural instabilities that takes place, like that of overaging, which takes place at higher temperatures, brittle intermetallic phase precipitations, and carbide reactions that take place at high temperatures. So apart from this, we have also discussed about the various creep deformation mechanisms, which involves dislocations by the aid of diffusion, which is known as dislocation creep, then diffusional creep, in which we have two types. One is Nabarro-Haring creep and second is Coble creep. So one includes that of lattice diffusion, and the other, that is the Coble creep, which involves grain boundary diffusion. So it occurs at slightly lower temperatures. Coble creep occurs at lower temperatures when compared to Nabarro-Haring creep, and grain boundary sliding, which takes place at very higher temperatures. So these creep mechanisms, deformation mechanisms, has also been discussed. Now we look upon into elevated temperature fracture. So elevated temperature fracture, it is of three types. One is rupture, second transgranular, and third intergranular. So these are the three modes of elevated temperature fracture: rupture, intergranular, and transgranular mode of fracture. Of which rupture, this occurs at very high stresses and high temperatures. Rupture takes place at very high temperatures and high stresses. So this is often accompanied by reduction of area approaching to about almost 100%. And this rupture, it is also associated with dynamic recovery and dynamic recrystallization. Dynamic recovery and dynamic recrystallization. And this type of fracture, it usually occurs at hot working, in the hot working range, and at very high strain rates. So rupture, which occurs at very high stresses and high temperatures, and these dynamic recovery and dynamic recrystallization, they are often associated with rupture. And this occurs in the hot working and at very high strain rates. So this is often not a creep dominated fracture mode. So we shall limit our discussion to this, and we shall proceed on to transgranular mode of fracture. So transgranular type of fracture, it occurs at high stresses and high strains. Transgranular fracture occurs at very high stresses and high strains. So this type of transgranular type of fracture, it is associated with the nucleation, formation of microvoids, formation of voids around the inclusions. Then these voids, they grow, coalesce to form a large crack. So transgranular fracture, it is associated with the nucleation of voids around the inclusions. These voids, they grow, coalesce, and form a large crack. And when the remaining cross section of the material, it is not able to withstand the stress or load, it results in failure. So this is about the transgranular type of fracture. Since this is a creep dominated fracture, we shall discuss about transgranular, as well as intergranular type of fracture also is a creep dominated type of fracture. So we shall discuss these two of elevated temperature fracture modes, because these two are creep dominated fracture modes. These two are creep dominated fracture modes, whereas rupture, it is not a creep dominated fracture mode. And in the case of intergranular fracture, this occurs at high temperatures than that of transgranular mode of fracture. It occurs at high temperatures and longer times. So this type of intergranular fracture, it also occurs by the formation of voids around the inclusions. It also occurs by the nucleation or formation of voids. These voids grow, coalesce, and finally leads to fracture. But this formation or nucleation of voids and growth of voids, all these are restricted to grain boundary. So this nucleation of voids, it is restricted to grain boundaries. Whereas in the case of transgranular, it is not restricted to the grain boundary. It occurs within the grains. In the case of intergranular, this nucleation of voids, growth of this voids, all these occurs along the grain boundary. So it is restricted to the grain boundary. So this type of intergranular fracture, it is similar to that of a brittle type of fracture. Whereas the case of transgranular, this type of fracture, it is often associated with some amount of necking and some amount of reduction in area and elongation takes place. Whereas in the case of intergranular, the appearance of this intergranular fracture is of brittle type of fracture. So the crack propagates along the grain boundaries. Whereas in the case of transgranular, the crack propagates through the grains. And moreover, this transgranular type of fracture, it is also similar to that of dimpled fracture or ductile fracture that occurs at room temperature. Because room temperature ductile fracture, it is also associated with the nucleation of voids which takes place at stress concentrations, which leads to triaxial state of stress. At this point, the voids, they nucleate, they grow under the action of the tensile stress. Then finally they undergo into a large crack, and finally the material undergoes failure. So this transgranular type of fracture mode, it is also similar to that of a dimpled fracture or a ductile fracture at room temperature. But the only difference between the ductile fracture which takes place at room temperature and transgranular fracture is the temperature. So this transgranular fracture which occurs at higher temperatures when compared to the room temperature ductile fracture, it is often aided by diffusion. So the formation of voids, growth of voids, all these are aided by diffusion. So this is the only difference between the transgranular type of fracture and ductile fracture which occurs at room temperatures. So this formation of voids, all these, it is aided by diffusion, or else this type of transgranular type of fracture, it is also similar to that of ductile fracture at room temperature. Now I shall draw the figures for these three types of elevated fracture, which you can clearly visualize them. So this is the type of rupture. So this is the rupture type of failure, where the percentage reduction of area, it almost approaches to that of 100%. And this takes place at higher stresses and higher temperatures. Whereas the second type is the transgranular. It is also a ductile type of fracture, but only difference is that this occurs at elevated temperature when compared to room temperature ductile fracture or dimpled fracture. So here the voids, they nucleate, and then these voids, they grow and finally leads to fracture. This is an example for the case of transgranular type of fracture, and this is rupture. And the third one is intergranular fracture. Intergranular fracture, which is almost a brittle type of fracture, where very little macroscopic plastic deformation takes place. Whereas the case of transgranular fracture, it is associated with some amounts of reduction of area, percentage elongation, and necking takes place in the case of transgranular. So this is intergranular type of fracture. So the growth of voids, formation of voids, all these takes place at the grain boundaries. So these grain boundaries, these grains separate at the grain boundaries, and this is a type of brittle fracture. So the voids, they nucleate at the grain boundaries, they grow, coalesce to form a crack, and then crack propagates along the grain boundaries and separation takes place. So this is the type of intergranular fracture. So this dark line indicates that the voids have nucleated, they have grown in size, coalesced, and the material undergoes fracture along the grain boundaries. So this is intergranular fracture. So these are the three types of elevated temperature fracture, and of which these two are transgranular and intergranular. These two are creep dominated fracture, where a rupture is not a creep dominated one. So we shall not discuss this type of fracture mode further. Whereas transgranular and intergranular, these two are creep dominated types of failure. Now we shall discuss in detail about the transgranular and intergranular types of failure. As temperature increases, there is a transition in the case of fracture for metals from transgranular to intergranular. That means there is a transition from transgranular fracture mode to that of intergranular fracture mode as temperature increases. So there is a fracture transition in the case of metals from transgranular to intergranular as temperature. This can be stated in a way that at low temperatures, grains and grain, when compared to grain and grain boundaries are stronger than grains. Therefore, a fine grain size material is stronger when compared to coarse grain size material. And at higher temperatures, grain boundaries are weaker and grain interior are stronger. So a coarser grain which is having a very small grain boundary area, it performs better, it is stronger than that of fine grain size material. And at temperatures when the strength of grain and the strength of grain boundary are equal, it is known as equicohesive temperature, that is ECT, equicohesive temperature. Equicohesive temperature is the temperature at which the strength of grains and grain boundaries are same. The strength of grains and grain boundaries are same. Below equicohesive temperature, fine grains are stronger because grain boundaries are stronger than the grain interiors. So having a larger grain boundary area, the stronger is the material. Above equicohesive temperature, coarse grains are stronger because grain boundaries are weaker above equicohesive temperature. And at that equicohesive temperature, both the grains as well as grain boundaries are same. The strengths of grain and grain boundaries are same. So as the temperature increases, the failure mode or the fracture, it undergoes a transition from transgranular. Transgranular means the crack propagates within the grain, whereas intergranular, the crack propagates along the grain boundaries. Since the grain boundaries are weaker at higher temperatures, so the transition mode, it changes from transgranular to intergranular mode. So apart from other factors, strain rate, it has an effect on equicohesive temperature. Strain rate indicated by epsilon dot, it is having an effect on equicohesive temperature. Lower is the strain rate, it lowers the equicohesive temperature. Lower the strain rate lowers the equicohesive temperature. That means as the strain rate is decreased, the transition to intergranular type of fracture mode increases to a greater extent. Our intergranular type of fracture mode is seen as the strain rate decreases. And equicohesive temperature, it is not a fixed temperature. It depends upon several factors. And depending upon the alloy, depending upon the composition, depending upon the microstructure, the stress rupture failures, they may be either ductile or they may be either brittle type of failure. Ductile type of fracture means which indicates that there is certain amount of plastic deformation that takes place. Some amount of plastic deformation takes place prior to and after fracture. As well as in the case of brittle fracture, there is no appreciable amount of plastic deformation that accompanied the fracture. So depending upon the temperature, depending upon the stress, depending upon the composition, depending upon the microstructure, stress rupture failures, they may be either ductile or they may be either brittle type of fractures. So the difference between the transgranular type of fracture and intergranular type of fracture with respect to stresses and temperature is transgranular type of fracture, it occurs at high stresses, whereas intergranular it occurs at low stresses compared to transgranular, and it occurs at higher temperatures and for longer times. Whereas transgranular it occurs at stresses greater than intergranular but temperatures and times less than intergranular type of fracture. Intergranular type of fracture, it depends upon the nucleation of voids, growth of voids, coalescence of these voids into a large crack. So these voids which form along the grain boundaries in the case of intergranular type of fracture, there are two types of cavities that takes place in the case of intergranular type of fracture. So in the case of intergranular type of fracture, you can see two types of cavities. So the fracture which takes place by the nucleation, growth of these cavities, it is known as cavitation creep. So two types of cavities are seen in the case of intergranular type of fracture. One is known as wedge cracking, or it is also known as W type of crack, W. And the second is known as round cracking, round or elliptical cracking, round or elliptical, it is also known as R crack. So these are the two types of cavities that takes place in the case of intergranular type of fracture. The cavities there are either W type and round or elliptical, because the appearance of these cavities are round or elliptical shape which form along the grain boundary edges, and whereas W type of cracking or wedge cracking, it forms at the triple points or at the grain corners. Triple points means the point at which three grain boundaries meet. So from this figure it can be clearly understood that this is the type of cracking which is seen, that is W type of cracking. So this is the W type cavity, wedge cracking, which forms along the grain boundaries aligned in shear, and this takes place during grain boundary sliding, and it occurs at triple points. So this is a triple point where three grain boundaries meet, 1, 2, 3, three grain boundaries meet. And in the case of R type or round or elliptical type of cracking, where we can see the voids which forms at the grain boundaries. They do not form at the corners, unlike the W-type cavities. They form along the grain boundaries. So these are R-type of cavities. So this indicates R-type of cavities. So they form along the grain boundaries which are aligned in tension. And W-type of cavities, they are formed along the grain boundaries which are aligned in shear. So this W-type cavities, they are formed along grain boundaries which are aligned in shear, and they occur during grain boundary sliding. And round elliptical or R-type of cracks which forms along grain boundaries aligned in tension. Aligned in tension. So these are the two types of cavities which takes place in intergranular fracture mode. And this intergranular fracture mode, it is promoted by the decohesion at the interface between the grain boundary precipitate and the matrix. Apart from this, other significant microstructural features also takes place during the stress rupture cracking. In the case of intergranular fracture, when it is observed, the grains in the vicinity of the fracture, they appear equiaxed. Even after considerable plastic deformation, these grains, they appear equiaxed. It indicates recrystallization has taken place in the case of intergranular fracture mode. Whereas in the case of transgranular type of fracture mode, when observed in the grain boundaries in the vicinity of the fracture surface, these grains, they are elongated in the vicinity of the fracture, indicating that there is no evidence of recrystallization in the case of transgranular. Whereas in the case of intergranular, the grains in the vicinity of the fracture appear equiaxed, indicating recrystallization has taken place. Whereas this is not seen in the case of transgranular type of fracture mode. We have seen the various creep deformation mechanisms which takes place at various combinations of stresses and temperatures. If one is able to predict which is the dominant deformation mechanism, that means which deformation mechanism is dominant, high creep rates or the maximum creep rate, it is determined for a particular deformation mechanism, that is the dominant one. Knowing the dominant deformation mechanism, we can design an alloy to be creep resistant. For example, of the various creep deformation mechanisms, we have like dislocation creep, diffusion creep in the case of Navarro-Herring and Coble creep. So if diffusion creep is the dominant deformation mechanism, changing the material to a coarser grain size, then one can lower the creep rates. So if diffusion creep is the dominant deformation mechanism for a particular combination of stress, operation stress and service temperature for a particular material in application, then one can design the alloy to be creep resistant by this increasing the grain size. And if dislocation glide is the dominant creep deformation mechanism, by placing obstacles to the dislocations like precipitates, dispersoids, one can lower the creep rate. So knowing the various deformation mechanisms that operate at a particular combination of stress and temperature, one can design a material such that it is creep resistant. So deformation mechanism maps, these are developed by Ashby and his co-workers. So by calculating for a particular combination of stresses and temperature, which is the dominant deformation mechanism, the boundaries, they indicate the same creep rate for two deformation mechanisms. So by looking at this, this is a very important tool. So by this one can design an alloy for the particular application to be more creep resistant, knowing the dominant deformation mechanism. creep deformation mechanism maps. So these are the deformation mechanism maps. These are the plots between stress versus temperature. So stress, it is normalized by the modulus, and temperature is the homologous temperature, which is the ratio of test temperature to the melting point. So the two axes are stress, which is normalized by the modulus, and homologous temperature. So these are deformation mechanism maps. So these are the plots between stress normalized by modulus and homologous temperature, which is the ratio of test temperature to the melting point. So this is the theoretical strength, and above which at very high stresses we have the dislocation glide, and at intermediate stresses we have the dislocation creep. This is the dislocation creep, and this is area represents the diffusional creep, where diffusion creep is of two types, that is Nabarro-Haring creep and Coble creep. So this is Coble creep, where at slightly higher temperatures we have Nabarro-Haring creep, NH creep, where the lattice diffusion predominates, and in the case of Coble creep, grain boundary diffusion takes place. So this is the various deformation mechanisms. So by knowing the test temperature as well as the service temperature as well as the stress at which the component or the material operates in a particular application, one can find out the dominant deformation mechanism. Accordingly, one can design the alloy to be creep resistant. So these are the plots which indicates the dominant creep deformation mechanism. So by plotting the strain rates also, so we have three variables: stress, temperature and strain rates. Knowing any of these two, the third one can be predicted very easily. So if Coble creep is the dominant deformation mechanism, then a material with a coarse grain size, it has a very low creep rate. The creep resistance of the material is higher. So as the stress increases, this is the intermediate stress level where the dislocation creep or the power law creep holds. This is the dislocation creep which occurs at intermediate stresses, and at higher stresses the power law is not valid. Power law breakdown occurs because the creep rates are very higher. So we have this diffusion creep and Nabarro-Haring creep. That means at low stresses and higher temperatures we are having this diffusional creep and dislocation creep at intermediate stress levels. And dislocation glide, it is still at higher stress than that of dislocation creep, and this is a theoretical strength. So this is the intermediate stress level, and this is the high stress level, and these are the low stress levels. So I shall give you an example for a particular alloy, that is a nickel based alloy, which is suited for an application, that is for the case of turbine blades, where the operational temperatures and the stress of the material that has to bear encountered during the service is known. So by knowing the combination of stress and temperature, so it falls in which region one can determine, that is it comes which diffusional or which creep deformation mechanism is a dominant one can be known. So knowing that creep deformation, dominant deformation mode, then one can make the alloy more creep resistant. So we shall look into the following example. So this is the deformation mechanism maps for the case of a super alloy, nickel based super alloy, that is nickel based super alloy MER M200. So these are the two deformation mechanism maps for this nickel base superalloy for different grain sizes. For grain size of 1 centimeter and for grain size of 100 micrometers. Okay. So 0.6. So these are the two deformation mechanism maps for a nickel base superalloy, that is MAR M200, which is used as a turbine blade. So in this you can see this crossed hatch region, it represents the turbine operation, where it is operated at about 600 degrees centigrade and the operational strain rates are in the range of 10 power minus 10 per second to 10 power minus 8 per second. And here we can see this is the turbine operation, the cross hatch region. This represents the turbine operation for a combination of stress and temperature. So this is for the same material, but the grain size is about 100 micrometers, and this is the deformation mechanism map for the same material, but the grain size is 1 centimeter. So by comparing these two figures, you can clearly visualize the dominant deformation mechanism for this turbine operation, that is a particular combination of stress and temperature, is the Coble creep. So this is the region, the Coble creep is the dominant deformation mechanism. By changing the grain size, to a more, when compared to this 100 micrometers, by increasing the grain size, the dominant deformation mechanism is not changed. It is again the same dominant deformation mechanism, that is the Coble creep. But by changing to a coarser grain, creep rates are lowered. So the material has become more creep resistant with increase in grain size than when compared to the grain size, which is of about 100 micrometers. So simply by knowing the which is the dominant deformation mechanism for the particular operational stress and temperatures, one can lower the creep rate. Since Coble type creep rate is inversely proportional, we have in that expression, creep rate is, we have the number of constants here inversely proportional to that of d cube of that of the grain diameter. So increasing the grain size, lower is the creep rate. Simply by shifting to a coarse grain size, the creep rates are lowered. And this we can see, this is the power law creep, that is a dislocation creep which has extended in this region, and this is the dislocation creep for this type of grain size. So everything this here, it represents the theoretical strength, and whereas this is the dislocation glide, this region, high stress region, represents the dislocation glide, and intermediate stress region represents the dislocation creep. And Coble creep, this is totally represents the diffusion creep, Coble creep and Nabarro-Harin creep. So here we have NH creep, Coble creep, and this is the theoretical strength. So even though these two diagrams, they are not to scale, but I want you to just appreciate, by knowing the dominant creep deformation mechanism, one can make a design an alloy to a more creep resistant. So this is one of the example for the case of a nickel based superalloy.